welcome. Thank you for being here. We are going to start with this workshop on the sewage system. First, I would like to thank the association for this opportunity to explain what we are doing as far as the management of the sewage system is concerned. First, around the table, I have my colleague, José Sala, and our consultant, Carlos Lopez. They will help me during the whole workshop, to organize the different sessions to make sure that they are successful. So before starting and to moderate a bit this workshop, I would like to know a bit what is the profile of the participant. We are talking about a topic with two different branches of the knowledge, urban hydrology and SIG world. So according to your profile, we will try to adapt and to balance a bit the discussion towards one area or another. And apart from my two colleagues, I have two other colleagues, Jordi and Sergi. They will also help. So if we need to have more speakers for practical things, we have lots of people. So first, I would like you to raise your hands if you're coming from the SIG world, if you know what is a SIG environment. Please raise your hand. Fantastic. Great. Because in the last workshop that we organized on this issue, we were facing lots of people that had no idea about SIG, so we had to make sure that they had a basic knowledge of SIG. Second question, people that have been working on hydrology and urban hydro system, please raise your hands. Well, we see that we have less people. So those with that knowledge, the second part of the workshop for this afternoon will be very useful and easier for you. For those that are not been working into urban hydrology, it will be a bit more difficult for you. So I'm sure that if you're here is because you have some interest in the general perspective of the urban sewage system. So the workshop is divided in two. So during the morning session, we are going to talk about the SIG world and how we can get data, collect data, and how we can structure the information that we are collecting about the urban sewage system to be able to do some management work during the morning. How we can build our network from the typology that we will see later on. Second session in the afternoon is once we have that topological network with all the data for the management of that network, how can we analyze the urban sewage system with the tools given by gvSIG and with the characteristic of our network. We will see how we can create some mathematic models to design and to analyze the operational side of our network. But it will be for the afternoon. Now we will start with the first session. We are going to build to design our network. So the first part will be a theoretical part. It will last more or less 1 hour and a half. And the second part of the morning will be much more practical. I think that you have downloaded the information and the documents that have been sent through the web page. You don't need to open gvSIG. We are going to try to give you the basic principles, and then for the practical part, we will use gvSIG. The theory that we are going to cover in the morning and in the afternoon will be posted and will be available at the end of the workshop anyway. So without further ado, we will start with this workshop. Do we need to manage the urban sewage system? Obviously, the answer can be found on these two pictures. If we are not managing what's underneath, what's underground, if they are not managed, well, those pictures represent a tropical rain in Guatemala, and this big hole has been well created because of a lack of management of the network, because also of another characteristic, because of a karstic land that was not well managed. This is why we need information, we need documents, we need to update that information for this sewage system network. So the first part will be dedicated to the introduction. First, we are going to see what are the objectives and what is the methodology that we are going to use. Then we are going to see a data model, a theoretical data model that we could use to design our network. And we will also establish some information import tools, and we will also talk about gvSIG functions to complete the model. Then with the tools that we find in the gvSIG environment with extension or with some application, we will see a bit extension of those applications to manage this urban sewage system. And at the end of the first part, we will introduce the second part for those that will stay with us this afternoon, or for those that are not coming this. The possibility to choose to come or not, thanks to this introduction that will be made about the afternoon session at the end of the morning session. So the objective of this workshop is to give you the capacity to visualize the potential of gvSIG for the management of the urban sewage system, and also to manage any network, any urban infrastructure network, not only for the sewage system. What we will be doing for the sewage system will also be doing for the supply network and any other structures, any other urban system with the Archnodo, Archnode model. We will be able to use it for other systems. So we will be using a scaling model. We will be able to design our network and to manage it and to have a broad view of what could be an integrated management system. We are going to use extensions, well, we are going to name them. So we are going to see, well, topology, street map, networks, typologies, allowing us, well, once we have built our network, we will be able to do some analysis and giving us lots of information about it. And the second part, as I was telling you, will be very practical so that you can, well, play with that application. To design our network, the first thing that we should do is to understand the data model, to use different tools to import the information, and finally, well, to complete the model, the data model. So what is this structure? The advantage to work in a free software environment is that we can use other extension, other open source software, and we can combine them. So for the analysis of urban sewage system and also for supply system, we can find a software that has been designed some years ago by the pollution agency from the United States. It's an open source software, and from 1971, in its first version, without the Windows environment. So from 1971, the Americans have been analyzing the urban sewage system with it, and also for the supply system. So that software is called IPA-SWMM. So if we are going to communicate that information with this other software, well, the data model should be designed in order to have a good communication of data. This data model should also solve the conflict that we might face when we want to confine the ARC node topology with the information requested by the SWMM. So here we are going to try to solve that conflict, obviously. So if we are using a relational data model, we will simplify the methodology and we gain a higher potential in order to collect more information. So it is very important when collecting data, and it's really helping us a lot when we want to collect that information. In databases, we can already have some pipe catalogs, register post, and the different drainage pipes, so we can have reports, and it's very versatile. And thanks to this new system, we will be able to work much better and to have a general idea of how it is operating. So here on this slide, you see how the topological model of ARC node is working, and thanks to which we will be able to manage all the elements of our network. So all the elements will be or ARC or node. So we will have to combine those elements of the network. We will establish a topologic relationship. If we want to include, well, the sewers, these will also be nodes, and they are going to be linked to ARC with the topologic relationship NA1 and NAM. Well, obviously, we can decide if we want to do it or not, because if we can define ARC and node connection, well, it's more than enough, obviously. So it's work that's already done, and that will be very useful. For ARC, we are going to define two different ARC typologies, or real or fictitious ARC. For real ARC, we mean any network element that really exists, and it's a physical element, the pipes of our network. By fictitious element, we mean elements that do not exist in reality, but that we are going to use for our hydrologic calculation, and that IPA-SWMM will be using. So it is sending virtual information from one node to another. It is a virtual ARC, so it's not existing, and the information given is also virtual. So we have real and fictitious ARC elements. and the relationship between the two is 1-to-1. It's a cardinal relationship. We have, for the node, we have different kinds of elements like wells, and wells, sewers, a spillway, etc., etc. All these, well, elements that we can find, well, on the spot. You know, these are all the nodes that we are going to find. And we have also a 1-to-1 cardinal relationship. Obviously, all these elements will be linked to state-associated table, in which we will be able to include the information about, well, a given time status. So we'll see its pure geometry, its situation, and all that information will be stored in the nodes. But also some information changing with time. In a sewage system, we have two types of information: the state, the situation, the state of the art of all these elements, and also the follow-up of those elements. As well, some elements are changing with time, they will be stored in a different table, and the cardinal relationship will be 1 to m, and we might have some end files of real information on those elements. Furthermore, well, we might also have and design some catalogs with the systems elements in order to simplify the management and to have access to, well, all the information available. For example, a well catalog, a spillway catalog, and each, and we can define and design our network according to our needs and design, well, the catalog that we might also need for the management of that system. The relationship of the catalog table with the reference table is 1 to n. So n elements of our table can be linked to one element in the catalog table. To finish with that data model, there is also a group of tables that we can see here in yellow. These are the tables that can manage the information given by the system in itself. So we have the event table. We have we can assign different events to the different elements, the different geometrical elements of our network. Oh, I forgot to tell you that in blue, node, arc, spillway, and a well are different layers for the database, and all the other elements in greens are tables. And so the event tables could represent an inspection service or a cleaning up service, a maintenance service too. All that information could be linked to the 4 blue tables, the 4 elements of our network, and we can fill those tables with information that we receive from the element that they are linked to. So it might look a bit complex, and it is. And it's a data model that has been designed for relational data management. We can also change the scaling model in order to be able to manage all that information without having to have 4 shapefile, and 40 table. It would be totally meaningless. It would be too difficult to manage so many tables and so many shapes. So this is the data model that is giving very good result, and we are going to reduce it to the Shape5 model that we are going to use to work today, so that at the end of the workshop, you will see that to manage it is very easy. And what is very important is to collect data, and with a very simple structure, it is easy to do. In the Shapefile environment, we will have the node shape and the arc shape. This is what we will keep. For the real elements, we will have an information table in relationship with the type of data contained in that arc. For this real element, we will also have a real data table. And for those that are linked to the node, we will have a single table where we will include all the data, and also for the status, we will also have a table. So what you have seen before can be summarized in 2 shapefiles and 4 more tables. And apart from those 4 tables, 2 are status table. And we will be able to feed this table with information, with data, and to update that information about the follow-up and the situation of the network. Apart from that, optionally, we will be able to manage, well, the other tables that are associated to the 2 main shape files, but this is something that's optional. You don't need to do it. We have those 2 layers with information and the 2 linked table. It's more than enough. If you want to add more, well, it's up to you. So this chapter is a bit more theoretical, as I told you. It's a bit more intense. And now we are going to explain the different fields that we need to have in our data model, so that we will be able to analyze the field and the node and arc shape, and that should also contain the other 4 linked tables. It will be available at the end of the workshop, at the end of the conference. So I wouldn't write anything. Instead of that, I would invite you to simply have a look, to listen. Don't take anything down. I mean, you will get all the information at the end of the workshop. So for our node shapefile, it is very interesting to have an identifier. It is a single identifier about the upper quota. The difference in and the different coordinates, x and y. And also the information that will be requested from the element table, and also for the EPA-S WW, we will also have some information about registry and about, well, the drains and the spillways, and this is an information that will also give us some information about, well, the quantity of water that is stored in the different nodes. And finally, we have this node layer that will need 2 other fields. The first field, in which we explain which type of node that we are using for the mathematical calculation, and the second field, what is this, the type of node in reality, the associated account, and another field that we will use to have hyperlinks and also to have a good document management. We have also two times the node and SWMM. We have those two fields because a node in our network, in our GIS network, could be different to what we find in reality. I'm not going to get, well, into details, but because we will see that in the afternoon. But a node in our reality might be, for example, a spillway, but mathematically speaking, that spillway should be an arc. Well, we will see that in the afternoon. I want you to understand the concept that a node in reality could be one thing, and in the mathematical model, it might be something else. So this is why we need that information. What is that node in reality, and what is mathematical behavior? And you will see with arc, it's happening exactly the same, but we'll talk about that later on in the afternoon. For arcs, we will have a single identifier. We will get information about the starting and ending nodes. To do it, we have different Giro processes with vital constants, elements. One more time, I'm not going to get into detail. And we will be able to get, well, some information about the starting and ending nodes of elements of our arc. We'll have some geometrical information. We will also include a field about the information that we get on the naming information that the mathematical model is using to calculate the speed of the water inside the network. So we are also using that parameter. It depends of the material that we are using in our pipes. We will also put some information on two values that EPA SWMM needs to calculate, and also the difference between the bottom of the well and the distance between, well, the different pipes in our system. And we'll be able to, well, you see here, well, the first and second element. Here we have the distance that we might have between the elevation, the lower elevation and the upper elevation. And at the end, when our pipe arrives to the next well, if there is a little step, a little jump, and we can also calculate this distance. The initial depth is the distance between, well, the initial well, the depth you see here on the slide, and we will also have the final depth, and then we have two other concepts. It is the distance between the first part, the upper part of the pipe, and the second part of the pipe, the lower part of the pipe. We need that information to manage, well, our system, because some pathologies, some problems that we identify is due to a bad coating of the pipe or a wrong traffic of the water through the pipes because of those differences in the elevation of the different wells. Now, I go back to the previous slides, and apart from the initial and end jumps, well, we can also collect other values to start with the mathematical calculation. We have another field, the shape of the pipe. for the shape of the pile, we need to combine it with the mathematical calculation model. And we will need to see the different section available in the program. We see here the different section, and we can check how the section available are the section that you see on the slides. So we have two slides representing those sections. And if our section is not stored in our program, we can always go to the last one. It is the custom section, the tailor-made section, and we can define, we can draw the section if we don't find the section in the program. Well, the software is an American software. It has been made with the section that are used in the American system. And in Spain, we have translated those sections into Spanish. It has been made by the Polytechnic University, Professor Martinez Soriano. And in spite of that translation, they have translated the software, the guide, and has been done very well. So thank you very much to Professor Martinez, and that can be used also in Latin America. But the name of the section are still in English. So, for example, the first one is called Rick Round. The second one is called Egg. So we keep the name in English because the sections are English, are American, and we don't find them in Spain. So there's no equivalent. So this is why we are still using the words in English. And we have also the collectors section where we have some downstream and headwater, and for the different, we have here the different drain pipe section. They are very typical in Spain, and we don't find them in the US, for example. So this is why, we would have to click on this last drawing and on this custom section, and we could define, that section according to our needs. But let's go back to the data model. In the data model, the shape of the pipe is the name in English, defining that name. If we want to put custom, then we will define in a table the geometries of that custom section pipe. We will also add a nominal diameter field to collect the information on that pipe, and we will be able to tag on the map using that field. So we will, for example, say it's made of concrete, a diameter of 40, rectangular, plastic, to be able to tag. So it's a tagging field for this model. If it is a custom section, we will identify the curve that are being assigned to that model. If it's a non-regular section, with this mathematical model, we'll be able to model, to design, non-regular section. So for custom section, we will identify what the shape of that section on the table. And as far as geometries are concerned, the calculation model includes four different geometries for our pipe shapes, and we will need to read the guide to know if we have to include the 4 types or less. So, for example, the circular geometry has only 1 type. Rectangular geometries has 2 geometries, geometry 1, the height and the width. We have more specific section that will have additional geometries. So for the different arc model, it might be interesting to get some information on the material. of the slope of the pipe. Well, it's not a field that we do need because the mathematical model is calculating it automatically. But for the management, it might be interesting to know the slope of that pipe to predict the different elevation, if they are if the slope is too weak or too steep, and we will get that information through GIS process. We will be able to calculate the elevation of the nodes and combine it with the depth of our pipes, for example. Another field, the profile pipe conduct, to know a bit what is the depth of our pipe. Is not a field that the model need. The EPA SWMM does not need it to be operational, but it might help us to know a bit what is the flow of water through those pipes. It might also be interesting to get some information on the return period that is associated to the pipe. In a network, that concept might be interesting according to the risk that we are ready to assume for the management. So it's not the same if we are dealing with a pipe in a very sensitive area near a school or near a high capacity area where the risk associated is minimum and we cannot assume higher risk, or a pipe that is located in a steep slope pipe with very few risks, and there we could allow that pipe to have a return period of 5 years, for example. So we can define a return period according to the management of risk that we are ready to assume. Other data that might be interesting is the street inclination. We will then use a GIS process to calculate the elevation of output and input according to the elevation of our arc. The depth, we have been seeing it before on the design, on the graph that we have seen before. Another interesting field here, we have according to the digitalization of our arc, if we have direct or indirect flow of water, and we will be able to combine that with the extension of the network, I would recommend to digitalize in the direct flow of waters, because then we will be able to use gvSIG icons with the little arrows, because, if we do it with the reverse flow of waters, then icon would indicate the direction of waters. So if we digitalize it according to the direct flow of waters, and the representation, the graphic representation, will be much easier to interpret and to understand. So here we see which type of elements are necessary and what is their mathematical behavior. I told you that the mathematical model and the real model might give different results. In reality, an arc is always a pipe. It might be fictitious or real. Here we have an auxiliary pipe, or an interceptor, or a secondary pipe. And in the mathematical model, an arc can be a pipe or a spillway or a pump. And we will need to define it to make sure that the mathematical model knows exactly what we are talking about. Well, in the afternoon, it will be further explained. And to end up with this, we also have a link field where we will use a text string and link to a directory. Well, these are the fields that we need for nodes. An arc. And now we are going to see what is the information that we can have in node arc and arc node and in the different steps. For the node data, well, these data are linked to the type of nodes that we are using to know exactly who owns that system. Well, in big cities, well, the city is divided in different sectors, and some pies might belong to one company and others to another one. So which type of section do we find? The kind of drain that are being used, the stretches that are being used, and all this kind of information, that physical information that might be interesting. Here we have another model that give us a approximative information. So that data is not used for the mathematical model, so we can well include the information that we want. It's just a reference that we can use, and it's happening the same exact for the ARC information. Well, the owners, the maintenance company, if we can avoid it or not, and information about the land where the ARC is located. If we can identify that some problems, some pathologies are associated to the land, if the land is made of this or that material, and thanks to that we could also do some analysis of the pathologies and bring some solution. Type of network, if it allows some cleaning, in which basin it has been assigned. You know that cities are being divided into hydrographic basins and more hydrographic information that we might need.
As for status data, we'll dash through this because what's interesting here is to get information on sediment, the type, the level, information on preservation status, the lower part, the walls, the top part. Also information on the status of the lid. This sometimes is a problem. There's some of the lids break, some protrude, some are sunk. If these lids break, you don't need to list this. It's simply you simply have to change it, replace it. But this information is always important. You need to check all of this. And as for arcs, we're basically interested in learning information on sediments, the information on the structural status, and some additional information that you decide is important. You have 254 characters to enter in this string. Very well then, this has been the boring part with all the different concepts of sewers. We've talked about the database and then DDFs and shapefiles. Here you see the different profiles and sections. We can skip through. It's curious that in the US you have many oval-shaped profiles, but here we tend to use in Spain the reverse egg shapes, like an egg upside down. Here you see the outline with the information we mentioned earlier. And here you see the different formulae based on which we will have all the information. Here you see the minimum elevation, the lowest part of our node, difference between the maximum elevation and depth. And we have this more complex formula which requires some knowledge in SIG, which would be the pipe slope. We need to know what the initial node top elevation is. We need to enter the maximum elevation of the destination node, end node, and we have to subtract the different minimum elevations or drops in elevations. We won't go as far as describing all of this in detail, but you have the formulae here so that since you master gvSIG, you can use these tables to operate. So you can go online and gain more insight. As for Shapefile, things can be simple, but this is especially important or useful with relational databases because there's so many operations that can be done. Very well then, so this theory is sort of a snapshot of what you can do once you have built your network, as we have just seen. And it's a way to manage all the different variables. We have different extensions or gvSIG elements that are available for connectivity assessment. We have this link. I think you have this already. You have these two screens, these two windows. Don't worry, we'll see this later on. We need to look at the flow field, and we can use this extension to learn how much network we have in the headwaters or downstream, and this will allow for easier maintenance and operation activities. It will allow for producing reports and so on. It's one of the benefits of using open software, i.e. you can make the most of what others have done, and even for a different purpose. Fran Peñarrubia, when he produced this, had roads in mind. He studied stop management, route and path networks, but since this is based on an ARC node topology, the extension can be replicated and used for a different purpose. It could be a tree network or a mesh network, and in this case for sewers, the sewage system. So we are benefiting, taking advantage of what other people have done who wish to share all of this. The same goes for the street plan. This is an extension which was produced by a company in Barcelona called Geodata, and it was designed to a different purpose. The idea was to design a plan to have a clear address and be able to use it as sort of a Google Street Map. So this extension that has nothing to do with the sewage system, and I believe my colleague will give you some more insight into this tomorrow, has been used to a different purpose. So it's absolutely great, and it can be extremely helpful to meet certain typical needs. I'm pretty sure tomorrow we'll cover this in greater detail. Then we have advanced hyperlinks, which is super simple but very, very useful. You link each feature to with a directory and have digitized absolutely everything. You can have videos, you can have QS, incidents, everything digitized in one directory. So, having one directory per feature, gvSIG becomes de facto a very powerful element to manage things. So, the days of visiting town halls and getting a pile of folders from a civil servant are over. And this, again, is super, super useful. I believe tomorrow you will get more details about this, but I just wanted to point this out very briefly. In closing, and I think we're sticking to the schedule. I think it's 12:30 noon. Yes, we'll finish this section here, and then we'll break for lunch. I just wanted to briefly tell you a little bit about the evening workshop. For those of you who are still interested, let me tell you a little bit more. One of the advantages of working with gvSIG is to be able to communicate with calculation systems for, say, supply networks, water supply, and sewage systems. This software was developed by the United States Environmental Public Agency. Has a great prestige regarding urban hydrology. You have EPA SWMM and has prestige because the software they've developed is very stable. But one of the drawbacks is that it doesn't have a GIS environment. So you have to use tools that makes this software, say, too small for big, large networks. So now we can make the most of this software in very large networks. When you have GIS information, you can massively export those to the calculation software and then go back to gvSIG to assess the results. And then SIG becomes also a very powerful analysis because EPA SWMM is very powerful in certain aspects. So both things can work together very well. Version 1.4 was launched a year ago, and we have been improving this. I think you have 1.72 now. We're already on version 2.0. This all works with Shapefile. It is more useful now. The first version only exported geometric data. The version you already have allows for exporting SWMM. Hence, we can control all the calculation settings. So we're just asking the US software to run and show results, and then we have a version 2.0. It's still a beta version. It's much more complex and allows for input and output with a configurable databases. I think you have version 1.72, as I said. So any data in gvSIG can be used with the IPA SWMM, and we're still using the geometric data for spikes, nodes, and so on of version 1.4. So this is where development stands, and this evening you will be able to see this in a more practical workshop. Going back to the slideshow I was showing earlier, you have all this calculation, and again, one node can be a well, a connection, but it can behave differently from a mathematical standpoint. I forgot to say that as for mathematical model, we have two layers. One would be drainage layers, and we can make the most of gvSIG's potential to see the runoff behavior in our urban basins through very specific methodologies we will be going into this afternoon, so we can see the rainfall and the amount of runoff and the amount of water that enters our network. And then we have the vertex layers, which is very interesting. So we see that there are some elements that are entered here, but apart from these layers, we have these tables here whereby one node can be, in reality, at least all of these elements here, say well, connection, so on, but mathematically it may behave differently. It could be a junction, a divider, a storage. I won't go into all of these now, but these tables are necessary because a node can be one thing in reality and a different thing as regards mathematically. And the same goes for an arc, which can be a stretch. And in the mathematical model, it could be different types of pipes, it can be pumps, it can be spillways, flow regulators, and so on. So we have this information, and our gvSIG can give us information, ortho photographs, land use, digital models of elevations, climate, drinking water supply. So many, many, many pieces of data in raster format, which will allow us to very accurately define our hydro model in our basin. In closing, in gvSIG we have project data, rainfall, climate, pollutants, should we wish to include this information, and so on. Of course, these results can be linked to an outcome table, both for arcs and nodes, and all this information under the orange line can be duplicated in case We are interested in simultaneously having real-time information and for future master plans, so we can duplicate this and use the information for forecasts and to learn real-time what is happening. You'll see more this afternoon. When you have the tables, you export through the interface. You decide SWIG or APNet, input, output. And the advantage, the benefit of this software is that it allows for dry profiles. You can learn the evolution of each of the elements in time. And that's it. Let us now break for 10 to 15 minutes, and we will resume this session and break for lunch at 2:30. Are there questions in the room? Okay, we might leave the Q&A round for later. Oh, there is a question at the back of the room. Please use a microphone. I see this model has been used more for rainfall a priori, because through this information we can gain insight into the basins. We've seen also we've also seen with brackish waters, the brackish water supply, right? Yes. Well, you have the stormwater model management, SWMM. It's a code for rain water, but it is true that we have the dry water flow, which would be for dry flows, of course. So that dry water flow can be brackish water. And that dry water flow can be modeled through SWMM through 4 demand patterns. So if you have an average consumption of 250 liters per inhabitant in a given city, through a very simple GIS system, you have around your node, say 50 persons. You can multiply this and we can modulate that average flow with 4 correction factors, say month from January to December. You can allocate each month a different then hours from 0 to 24 hours, then day factors, say from Monday to Sunday. So at the end of the day, to model sewage water, you can perfectly do so if you know the demand patterns in any given area. So because the amount of brackish water is always lower than rainwater. So this is interesting. Sometimes sometimes you might have a mix-up with the rainfall and brackish water. I totally agree, yes. Well, also with gvSIG, you can very accurately estimate the amount of sewage water. often for rainwater, you have a 2 hour span, but you don't enter a time setting. So you don't. This would be useful for long-term simulation, whereby you can introduce correction factors, and you can know what the actual rainwater was. You can you can know the rainfall of a specific day and time. Thank you. All right, 10-minute break. See you at 5 to 1. Thank you.